Hello friends, this is Mohammed. I'm starting my course on applied deep learning. I'm using the slides of Professor Ali Berihi, the professor of electrical and computer engineering department of University of Toronto. Okay, I hope you enjoy it and if you had any issue, please email me and yes. Okay, we are going with chapter 1 Part 1 Preliminaries. Okay, uh, now as you may have followed the news, you have received lots of notification and news about deep learning, about machine learning, and it's an unbeatable champion. Uh, in lots of tasks, lots like image classification, which we have some images and we want to label them, or restoration, segmentation, and lots of things, it surpasses the human capabilities. It means if we have a human and we have an AI powered machine, it would surpass the human. Okay, and it can, as you can see, ChatGPT and lots of LLMs, large language models, uh, they can create human-like conversational dialogues, and uh, yes, they have improved a lot. Okay, one of the first problems in artificial intelligence was image recognition. That we wanted to recognize what in an image. The Jan LeCun, one of the pioneers of AI and machine learning, proposed LeNet in 1998, and in 2010, ImageNet started the annual contest, and the AlexNet, then VGG, and GoogleNet, and finally ResNet were the winners. But you should note that currently we have much deeper and advanced neural networks in the field. We will get what these networks are uh, in the following of this course. In 2015, Microsoft announced their deep neural network beat human accuracy, and after Microsoft, Google has beaten human accuracy too. And now we have ChatGPT. You have access it with chat.openai. It's free, and lots of other LLMs that are now free and available. You can use them. Uh, yes, I prefer to skip this part because I want to. I have assumed that all of you are somehow familiar with the achievements of artificial intelligence and especially deep learning. So I'm going to skip these parts. Uh, okay, but we have we have heard what is deep learning, machine learning, or you may confuse what's the difference between these terms. Deep learning is a subset of machine learning that uses deep neural networks to learn tasks. I will let you know what is deep neural networks in the future. It's somehow soon to know it. Yes. Okay. Uh, we are going with the next section of this slide. Yes. Machine learning. Uh, when we I want to get you familiar with what machine learning is. When we want to solve a problem, we have two general approaches. The first approach is to solve it analytically. For example, we know what is the formula of a physics equation, and we use it and we solve it with mathematics analytics. But sometimes we don't have the analytical exact formulation, so we have to use data driven algorithms. And in machine learning, we want to solve the infeasible problems. By infeasible, I mean the things that are infeasible to solve math, by pure math and by analytics, not by data. And as I told you, there are some physical equations that we can use, like this one that you may have seen in your courses, in your undergrad courses, or may have seen these equations in your high school in physics. For example, the motion of a projectile. If you want to solve it analytically, you have x equals to v times t and blah blah, and you can solve it as you can see in the formulas. But we don't want to solve things analytically in machine learning, because lots of times we do not know the analytic formulation. So in machine learning approach, we want to conduct the experiment for I different times. It means we initiate different velocity vi and different heights that we name by h of I, and we then measure the horizontal distance d of I, and we then assume that d of I and the pair v of I and h of I are related via a predefined function. For instance, we assume d of I and the pair of v of I and h of R are related as d of I equals to a linear function of these two parameters, and we then try to find the optimal values. But note that how can we be sure that uh, how can we compare the value that is conducted that is derived from this uh, linear function and the original value of d of I? We should have a loss function that measures the difference between the predicted value and the actual value. So yes, here is the loss, which is the sum over all of the losses of each instances. Okay, and then we want to minimize the loss in a point that we have the most same predicted values as the actual values. So we want to argmin loss of w0 and w1. Yes, in terms of w0 and w1. Yes, and the machine learning derived distance is not as accurate as the analytic one. Why? Because how do we know that it is linear? Maybe it is not linear, and you know from your high school or undergrad that it is not linear. We have seen the formulation in some few slides before. And yes, and in the assignment that Professor Brahe gave us, we had an example. Maybe I will discuss this example in the future about this exact difference between formulation in analytics and in machine learning. Okay, we have three main components in machine learning: first dataset, then model, and third loss. Dataset is data, all of the information that we have from the real world, or not necessarily real world, the information that we want to find the hidden things inside it. Second is the model. It is the thing that helps us. It is the most important part of a machine learning component. It is the brain of machine learning. Model tries to learn everything and tries to find the hidden, the hidden parts of data. It helps us to predict everything. And third is a loss. Loss function tries to it's a function that we want to minimize it. The lower the loss, it means that we are nearer to our uh, actual values. So if the loss is low, we are happy. If it is not less, we are not happy. So we should try to minimize the loss when we go up. Yes, these are some recap. I think you are already familiar with um, vectors and matrices. I will skip these parts. Uh, yes, and also for a dataset, we have some data points that maybe it is labeled or maybe it is not labeled. Uh, yes, a dataset always consists of some inputs and it may consist of some labels which are outputs. If it is labeled, it is supervised, and it is not labeled, it is unsupervised. But yes, I will let you know more about what is supervised, unsupervised, and even semi-supervised, and yes, self-supervised. Uh, okay, I'm going to yes. As I told you, supervised learning means that dataset is labeled, and unsupervised learning is that we don't know the outputs and we have to um, we have to learn the features of data point X by investigating a set of its samples. Okay, I think yes, I think these things we can skip these parts. Okay. As I told you, a dataset is of form d equals to x of I, that I varies from 1 to I, which is I is the number of all of our data points. It is the dataset length. So please note that we want to find v in which x of I equals to v times a of I. We don't know v nor a of I, so it is an unsupervised learning problem. And we had a solution named PCA, which was principal component analysis. I will talk about it in the future. Okay, then we have model. Uh, so, model. What do you think of model in physics? Model is something that simplifies some of the realities of the world, but it is somehow different here. It is a parameterized function that is used to tell us what is the relation between the input x and its label y. Okay, uh, please forget unsupervised learning, because you may say in unsupervised learning we didn't have label. So what is model in that formulation? I will let you know in the future. But now assume the supervised learning. You know. So uh, if you consider our previous example, uh, we can have d equals to w0 times v plus w1 times h. So in this formulation we can rewrite it as we had in the linear algebra as w transpose times x. In this example, w transpose is our model. In better words, it's the set or its dictionary of all of the parameters of our model, and it's the heart or brain of our machine learning model. Okay, I'm going to escape this part because I think these parts are not that much interesting. Okay, so models have parameters it means that the parameters should be tuned. We have to find the best hyperparameters and learnable parameters that make this equation for us true, because I mean we have to find best parameters and hyperparameters in a way that the loss would be minimized. Uh, okay, hyperparameters. Uh, the hyperparameters are the parameters that are not to be learned. We have to specify the model explicitly. You know, how do we know if the equation is in order p? What is p? And you know, in the polynomial model, we don't know what is p. Is it 2 or is it 1 or is it 10? You know, in the previous example, we have assumed that p is equal to 1. Okay. You may think, how can we tune hyperparameters? I will let you know in the future, but in one word, with validation. Okay. Okay. And we have some other parameters that are named its W transpose in the previous slide. So we have to learn them, and by learning I mean to minimize the loss function, and we have to find the best W's or the W transpose matrix that minimizes the loss function. And the third component is loss. It is the difference between the output of the model and the truth table. Okay, for example, this is a loss function that we call it energy of the difference. It is a squared error, which finds the difference between z of I and y of I, and power it to 2. It is another loss function, which is an indicator error. It is the occurrence of error. It counts the predictions that are not equal to the actual values. So we have seen all of the components of machine learning, and now we want to know how can we solve machine learning. We have to tune the learnable parameters, and when we tune the learnable parameters, we are finished with our machine learning algorithm, because we have a model that can predict the world in an accurate way. Okay, we have and you may have heard of the term training of the model, and it's in simple words it means to tune the learnable parameters. Okay, and I told you that classification means to find the correct label of an input. Usually it's image, but it can be text and many other things like audio. Okay. Okay, in classification, for example, we have this image, and we want to we have some pixel values, and we want to know if it is dog, it is cat, it is human, and we call dog by 0, cat by 1, etc. But we have binary classification. It means it is 0 or 1. For example, it is dog or cat, or dog or not dog. And yes. Okay, these things are okay. We now reach the perceptron. Perceptron is a linear classifier. It is an affine transform which you have seen, which you had seen it in your linear algebra course. It classifies using the sign of this transform, and yes, you can see the formulation here, and yes. Okay, And if it the activation or this function works in a way, if its input is more than or equal to 0, it is 1. Yeah, well, and if it is not, else whether it is 0. Okay, okay, and I will skip the history. Sorry for that. You can pause the video and read it. Uh, okay, okay, and okay. Now we have learned that the main component of machine learning uh, are a model, data, and loss function, and we have seen the classification example, and we want to know what is tuning the learnable parameters of a model. It means training of the model, and note that we have um, two you know there are two parts. One part is discrete randomized variables, and another one is continuous. It means if it is continuous or discrete, and it's the difference between integral and summation, as you know. It's not something important, and probability theory says that in discrete we can write expectation in form of summation of x times p of x, and in continuous we can rewrite it in the same way, but integral instead of summation. Okay, and we have a lot of large numbers that if we consider a random sequence x1 to xi, we call it independent and identically distributed IID with x from p of x. If x is the x's that are generated independently, all with the same distribution p of x. And law of large numbers, what is it? If we assume that x1 to xi is an IID sequence with x derived from p of x, then we have 1 over I sigma of xi will converge to expected of x as I converges to infinity. In simple words, if we arithmetically average too many samples of a random process, we get a value very close to its expectation. Okay, and yes, okay. As you can see in this figure, we want to find the correct function y of x, but what is the best one? The best one is the one that is most similar to the real function. It means that in mathematical words, it means that it is very similar to it is very similar to our main function. It means that the loss is very low. Okay, so we should define the risk, and we want to minimize the loss, and okay, we should minimize the risk, as you know, and I think is our yes, as you can in empirical risk minimization, or ERM, we want to minimize the loss or risk. So we have to find a W, which is the argument of r hat of W, where r hat of W is the risk or our loss function. If we replace the law of big numbers, we can see this function. So if we want to wrap up, we have this model and loss function. We determine the empirical risk using loss function. We train the model by minimizing the empirical risk, and yes, that's it for this part. Okay, we continue with the other slides. We understood what is perceptron. In binary classifier, we have indicated our error indicator as loss function, and we have understood what is perceptron. Okay, we should minimize the empirical risk, but the important thing is that we have to find the argument of this empirical risk. How can we do it? We should do it with optimization. What is optimization? We will discuss it in the future. Okay. What are the perceptrons? Are the Rosenblatt's perceptron. It has no bias, so it can be computed as W transpose times X of I, and if it is more than or equal to 0, it is 1, and else it is 0, and yes. And we update it with its sign, as you can see, but usually it's not very good. We will discuss it in the future. So please note that we should have bias. Bias helps us to add one dimension to the data point with the value always equals to 1. Okay, the perceptron algorithm tells us that we should compute zi equal to w transpose x of I plus b, and then if it is if we have passed it through function s, which tries to find if it is equal to or more than 0, it is 1, and else it is 0. And if the output of this s function is not equal to the actual output that we expected, we should update it in this way. The new w equals to w minus sine of z of I times x, and the bias should be updated in a similar way, that is b is equal to b minus sine of z of I. Okay, and you can see why this algorithm works, and why this algorithm really tries to minimize the empirical risk function. If we know that z of I is w transpose x of I, and we know it's bigger than 0, and if y of I is 0, we update it in this form that you can see. And in this equation, w transpose in time t plus 1 times x of I equals to w transpose minus x of I times x of I, because we have updated it here. As you can see, we have updated it in this format. So w transpose x of I minus norm 2 of x of I is x of I, and we already know that it is less or equal to w transpose x of I. So the algorithm pushes the weight somewhere that z of I could get negative. You know, the x of I is less or equal to w transpose x of I. Yes, that's it. Okay, it makes sense that in each iteration w gets modified towards the right direction, but can we guarantee that this algorithm always converge? Well, let's try some examples. In this example, you can see that yes, it is a false conclusion. It means that a false initial conclusion is that perceptron can realize any binary function, but it is easy to see that this is not the case. If we have XOR, it is nonlinear, so it cannot do it. XOR is not linearly separable, and perceptron can only classify linearly separable functions. At this point, it was concluded that perceptron should be replaced by some other model in order to learn nonlinear function. Finding models that learn nonlinear function led to the birth of representation learning, but we don't need to study it since learning solves the problem. Okay, multilayering perceptron helps us to solve this problem, and as you can see, if we have 2 layers of perceptron, now we can learn it with 3 perceptrons. So the first perceptron and second perceptron classifies, and the third perceptron intersects the 2 regions. Uh, and we can learn any binary function using a network of perceptrons, and it is the birth of neural network. And yes, it's getting more interesting. Uh, we can look at perceptron as an artificial neuron. We can learn any complicated function when we have a network of these networks. We can when we have a network of these neurons, we can call it a neural network. uh, but why do we care about binary functions? Why don't we learn other type of functions? Yes, we are going to do this. In real world, inputs are not uh, necessarily binary, and when we want to do it, we should have a multi-class classification. uh, we can do it with binary classification also. It means that, for example, if it is of class 0, it is ended, but if it is of class 1, it may be of class 0 or 1 again in the next hierarchy, in the next steps, I mean. And yes, okay. And we have also regression problem. It means that necessarily there are not classes. You may want to predict, for example, the value. The value may vary in a lot in big range. It may not be an integer. Uh, so uh, when we call this problem regression instead of classification. And yes, you can see that it has the same hierarchy, and we can do regression as well as it's similar to the classification problem. And in real valued functions, we can also approximate them with a network of perceptrons plus a linear transformer. Uh, a linear transform. And a network of perceptrons seems to be a very sophisticated model. It can learn any classifier, it can approximate any function. And we want to minimize this. In universal approximation theorem, given a function g and epsilon which is bigger than 0, probably near to 0, there exists a neural network f with parameters w that we can satisfy this uh, inequality. So it seems natural to train them for our learning tasks, and is a network of perceptrons is a special artificial neural network, and we now formally introduce artificial neural network in the rest. Okay, we're gonna continue with section 4 of chapter 1. We also artificial neuron. Perceptron that we talked about before is a special type of artificial neuron, and in general, artificial neuron is something that you can see in this picture. There are some x's as input, there are some weights on the eights, and we have a bias. So we have a linear function here, w1 times x1 plus something, and up to wn xn plus bias, and all of this term goes into an activation function called f. This activation function can vary, and the final output is y. We have n plus 1 learnable parameters y because we have n w's and plus 1 bias, so we have n plus 1 learnable parameters. Okay, I told you what are these things, and now we want to talk about activation. The most popular type of activation is ReLU. It is 0 when it is negative, and when x becomes non-negative, it is an identity function, as you can see. So ReLU of x equals to max of x and 0. Another popular one is sigmoid activation function. It is non-linear. ReLU is you can see here ReLU, and now we can see another nonlinear function, which is a sigmoid function. It is equal to uh, it is equal to 1 over 1 plus e to power minus x. Another one is hyperbolic tangent and soft ReLU, and there are other functions too. Okay, so up to now we can define a neural network or artificial neural network as a directed graph that connects a set of inputs to a set of outputs, and the nodes of this graph are neurons whose activation functions are known and whose weights and biases are learnable. Okay, and we want to talk about the depth of a neural network. The depth is the longest path between an input and the output. If we go from x1 to f3 to f2 and to f4, it is 3. Can you find a longer path? No. So the length so the depth of this neural network is 3. Please note that you are not going to count f4 to y, so you should start from input to the output neuron, but not counting f4 to y edge. Because if you count it, for example, you would get 4, which is incorrect. The correct depth of this neural network is 3. And what is deep neural network, which we talked about deep learning at the start of this session? A deep neural network is a neural network whose depth is larger than 2. It means equal or larger than 3. So, because the depth of this network is 3, which is larger than 2, it is a deep neural network. Okay, we have layered our architecture. Each when we put these things in alongside each other, we call it a layer. What is a layer? It is a subset of neurons that are in the same distance from the input. How can we calculate the distance? I told you the longest path from input to that part. Okay. In neural network, we have a layered architecture, and there are 3 types of layers. Input layer that only contains inputs, and we have a no neuron here, so we should not count the inputs. We should not count the input layer as neural part. It is not neuron. Okay, it is a part of the neural network, but it does not contain neurons. The output layers that contains the neurons computing network outputs, and the hidden layers that contain neurons and that are between the input and output. So a neural network in a layered architecture has 3 type of layers, that 2 of these 3 are neurons, and the input layer is not and does not have any neuron. Okay, so the depth of a neural network can be calculated as the number of hidden layers plus 1. Why plus 1? Because if we only count the hidden layers, we did not count the edge from input to the first hidden layer, so we should plus it by 1. And so we know that the depth of deep neural networks should be more than 2, so we can say that the number of hidden layers should be more than 1, so we can call it a deep neural network. Okay, and we can implement an XOR, as you can see here. It can be modeled as you can see it is a 2-layer neural network with one hidden layer, so it is not a deep neural network. It is a shallow neural network, which is opposite of shallow is opposite of deep. Yes. Okay. We talked about these things before. Oh, and now I want to talk about more about hyperparameters. Hyperparameters are not learnable. It means they do not have gradient. Oh, I didn't talk about gradient that much, so you will know more in the future. Anything that describes the architecture is hyperparameters. For example, the depth of the neural network, the activation functions you use, and blah blah. Any other thing that you can think of that and is not learnable is a hyperparameter. But the weights and biases are the learnable parameters. Okay. 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 You can count the number of you can count the number of learnable parameters. For example. Here you have here you have neurons 1, 2, 3. Each of the F1, F2, and F3 has 2 inputs. They have also one bias, so 3 times 2 plus 1, and also the last one, which is F4, has 4 inputs, so it has 4 base plus a bias that we always have it. We assume that we always have a bias, except that the case that, for example, the question explicitly says that we don't have, or we want to explicitly implement something that does not have a bias. Okay, so it has 14 learnable parameters. Now, when we are using deep neural network, we are talking about deep learning. Deep learning is the thing that you always hear about in the news if you follow news, because some people do not follow it. Okay, in machine learning, we talk about any model, any loss, and any data set. In representation learning, we talk about models that can describe nonlinear function. For example, it concludes deep learning, So deep learning is a part of representation learning, and yes, and the best description is as follows. Deep learning is a part of representation learning, and representation learning is a part of machine learning. By part I mean a subset. Okay, and I think we have talked about all of these things that are on this slide, and there is no more thing to talk about at the moment. In the next slide, I want to talk about gradient descent. Yes, please follow me to know more about what is gradient descent. It is the most important thing that we have. Geoffrey Hinton, you may heard of him. Okay, we are on section 5 of chapter 1. We have talked about lots of things, but we have not talked about optimization. Where we have said that we should minimize and optimize this empirical risk, but we had not said how should we do this. Okay, in accurate approximation with only one parameter, we need G grids. It means if we have D parameters, it means that W is of shape R power D. We need G power D grids to get an approximation with the same accuracy. For practical neural network, the D is equal to D to power 5, so it is impossible. You know what I'm saying? Okay. Okay, we need to have an optimization algorithm. So why? Because if we have D equals to, it means we have 100,000 parameters, and we have some grids. It would be G to power of 100,000. G is the grid, so it would be very, very high. Okay, so we need an optimizer. We should start from an initial point. We should move for feasible number of steps to minimize the empirical risk. And here is an iterative approach. We should continue in a while and determine a vector mu based on R, which is empirical risk and update weights and updated deviation, which is the stop criterion when we want to stop our while loop. And yes, and now we want to introduce gradient descent algorithm. It gradient descent algorithm says that this mu that you see in this slide should be proportional to the negative of gradient at w in time t minus 1. Okay, and we have to know what is the derivative of function that you can see. I think you had these things in mathematics, so I'm going to skip this part. Yes, skip this part, skip this part. Yes, I think you're familiar with the minimum, maximum, extremum derivative of derivative 2, derivative 1. Yes. Okay. And also multivariable functions. For example, if you have f of w and the w is w1 to wn, we can take the derivative with respect to each variable. For example, we can take the derivative of w0 with respect to you can take the derivative of f of w0 with respect to wn, and this is what we call partial derivative. Okay, and finally the derivative of y would be the sum of all of these partial derivative, as you can see in this line. Yes, and yes, you can see matrix multiplication here. We want to review the gradient of a function here. We have seen this summation in the previous slide, and you can write this part as a function, or you can write this function as another matrix, and you can define the gradient of f of w0 transpose as follows, and yes, you will reach this equation that we call a gradient of f w0, the gradient of f at w equals to w0. Yes, and yes, I think you already know these things that were here. If you want to have the gradient in a contour level, the variation of y is the inner product of these two vectors. I think it's also clear here. Yes, I think it's yes, it's you had it in mathematics 1 or 2, 1 I think. Okay, this lecture became somehow longer than I expected, but we are on our last section of chapter 1, so be patient. We are going to finish this slide in I think 7 minutes. Yes. Okay, if you want to move a tiny step of fixed size, for example, the Euclidean norm of w equals to epsilon for some small epsilon, how can we move such that y maximally increases? Well, we need theta equals to 0, meaning that we should move in the direction of the gradient. Alternatively, please pay attention, the function decreases maximally if theta equals to p, or if we move in the direction of negative gradient. So it is the proof of gradient descent. It is saying why optimization in the way that we optimize based on gradient result works. Okay. Okay. And also we can relate it to the second order derivatives of the function. At maximum, Hessian matrix is negative definite, and the at minimum Hessian matrix is positive definite. Okay, and also at saddle point Hessian matrix is neither negative nor positive definite. Okay, and what is Hessian matrix? Hessian matrix is a matrix of all second order derivatives. So we want to derive second derivative of f with respect to w1 and w with respect to w1, w2, w1, wn, blah blah to the end. It is a Hessian matrix. Yes. Okay. It was just a reminder, we are not going to use Hessian anymore. Okay, the gradient descent at any point w0, if you want to move in a direction that the function reduces, the best direction is negative or gradient at w0. So we can complete our optimization as follows. We can, as you saw, we had a mu 0 or mu of t, sorry, and we replace this mu with eta gradient of r at time or at point t minus 1. And what is this scalar eta? It is a step size, and we can call it learning rate, because it is a rate that we say we are going to learn this parameter. It is maybe a weight or a bias. Okay, and the behavior of gradient descent. Can we always use gradient descent? Yes, because yes, because we can use it in all the cases that we had a convex or even non-convex differentiable function, but we cannot use it only in case that it is not differentiable. Okay. So if we have two cases that we have the problem with non-differentiability. The first one is a function that is continuous but non-differentiable. The second case is that the function is not even discontinuous. Okay, we are going to get deeper into each of these two cases. Okay, the radio function, as you can see, is continuous, but it is not differentiable. We define the subgradient and use it instead of gradient. We can take the slope of a line that lies below the curve at the point. And so yes, and the gradient is somehow infinite. We can only rely on the sign of variation. We always avoid such elements in our model and loss, and you may recall that we discourage the choice of attributional loss in the perceptron mesh. Okay, we are going to assume that we have handled differentiability, and if you okay, so here we have a handle two parts. The first one is ReLU, that is non-differentiable, but it is continuous. We can define a subgradient and use it instead of, you know, in when it is negative it is 0 and it is positive it is 1, and in the middle we can we can assume subgradient. And another one was step function, which is not continuous, and we only rely on the sign of variation. It means that we always avoid such elements in our model and loss. And okay, and now, does gradient descent always end up at a minimum point? We should know if it converges or not. Okay, if we set epsilon very small, the algorithm stops when the gradient is close to 0, for example when we are at maximum, minimum, or an inflection or saddle point. Let's see how the algorithm behaves when we get close to such point. Okay, when we are around the maximum, if we're exactly at maximum, then the algorithm stops, but in reality we land somewhere around it. At such point, the algorithm always pushes us towards. Gradient descent practically does not get into a maximum. Yes, because we are searching for a minimum, and you know we are going in the direction of negative of gradient. Okay, when we are around a minimum, the algorithm always pushes us towards the minimum, and when we are around an inflection point, if we are exactly at an inflection, then the algorithm stops, but in reality we land somewhere around it. At such point, the algorithm always pushes us somewhere else. So the gradient descent practically does not get to an inflection. Okay, so can we extend this conclusion to saddle points? Yes, but with a bit of caution. A saddle point's function is maximized in a direction and minimized in another. So for a saddle point, we can conclude if we are exactly at a saddle point, then the algorithm stops. But in reality, we land somewhere around it, like the previous ones. If at that point the gradient has a component in the direction that the function is maximized, then the algorithm pushes us towards. Can it happen that we do not land at such point? Thinking with an engineer's mind, not really. So we could say gradient descent almost never gets stopped at, you should pay attention to almost never, but we are talking in practical words, so almost never gets strapped at a saddle point. Okay, okay. So the conclusion is that the gradient descent almost never gets trapped at a point that is not minimum, but it does not mean that it always converges. If we choose the good learning rate, then yes, we can say it would converge. And we should know how small it should be. With large learning rates, the algorithm starts oscillating. With extremely large learning rates, the algorithm diverges. Okay, it is very important. Okay, okay, so if we are in multidimensional function, it is the same in different axes, and also one might suggest that we use a vector of learning rates. For example, we can in each direction we have a special learning rate or eta. It's not going to be easy, as you can see. So we have a trade-off. Like all other problems in the world, we can choose a large learning rate, so the gradient search converges faster, high convergence speed, but we can also diverge. Okay, we can also use a small learning rate, so the gradient descent converges slowly, very slowly, low convergence speed, but the chance of divergence is now very low, and so we have low divergence rate. If we are patient, we can choose a small learning rate. It is safe, but if the empirical risk is convex, then yes, but with non-convex risk, not always. In convex function, as you can see, you can see the convex functions means that yes, this equation is always true, but we are not need the definition of convex function. Yes. Okay, in convex function we don't have disjoint local minima, so we are sure that converges to the global minimum even if we choose a small learning rate, but in most empirical classes they are non-convex. If you have multiple disjoint local minima, the gradient descent converges to one of them, but not necessarily to the global one. to a small learning rate can leave us in a bad local minima, and initial larger learning rates can take us out of bad local minima. So it is or it's an overall look of what we had, and it is a summary of gradient descent. I hope you enjoyed the class. Please follow us on the next chapter of this course. Thanks.